All right, so here we are in 11.4 on curve sketching techniques. So we're going to be modifying the graphing strategy, using the graphing strategy, and then modeling the average cost. So modifying the graphing strategy. So the first version we looked at in 11.2 made no mention of asymptotes. So including information about asymptotes is actually going to produce the following and hopefully final version of the graphing strategy. So here we go. We have step one. We're going to analyze f of x. So we're going to find the domain of f. We're going to find the intercepts. We're going to find the asymptotes. Then step two, we're going to analyze f prime of x, the derivative. Basically going to find the partition numbers for the derivative and the critical numbers of f. Construct a sign chart for the derivative of f of x. And then determine the intervals on which f is increasing and decreasing. And then find local maxima and minima of f. Step three, we're going to analyze the second derivative of f, and we're going to find the partition numbers for the second derivative. We're going to construct a sign chart for the second derivative, determine the intervals on which the graph of f is concave up and concave down, and find the inflection points of f if there are any. And then step four, we're going to sketch the graph of f, draw asymptotes and locate intercepts, locate the local maxima and minima, and the inflection points, and then sketch in what you know from steps 1 through 3, and plot any additional points as needed to complete your sketch. So it's quite a bit of stuff to do. So what we'll do is we'll start with this one. And so again, we're going to use that graphing strategy to analyze the function f of x equals 2x over 1 minus x. And we're supposed to state all the pertinent information and then sketch a graph of f. All right, so what values are going to work for our domain? So our domain are going to be basically all reals except for x equals 1. So we can say all reals except x equals 1, because if we plug in 1 here, we get 0 in the denominator, and that doesn't work. Okay, so now if we plug in and figure out where the numerator is 0, 2x equals 0, well, that gives us x is equal to 0. So that's going to be an x-intercept. And our y-intercept then is also going to be, guess what? F of 0 is going to be what? Well, we plug in 0 here and 0 here. We get 0 over 1, so we get 0. So we get 0 over 0. And that's going to be our y-intercept. Now, asymptotes, here we have to go back and remember, okay, so we're looking at the power. So we rewrite this as 2x over a minus x plus 1. They both have power of 1. So since they're equal, our y equals our values in front, 2 over a negative 1, which is a negative 2. That's going to be our horizontal asymptote. So we can say over here, y equals negative 2 is our horizontal asymptote. Okay. And what do we know? Because we can't have x equals 1, we have a vertical asymptote at x equals 1. Okay. So now we've got the horizontal, the vertical, and all that stuff. So this should be everything I think they asked for in part 1. Now, part 2 of the strategy said, okay, now let's take the derivative, the first derivative. So f prime of x. All right, so if we take the derivative here, now what we're going to do is we're going to have the bottom. And again, I'm going to rewrite it as the minus x plus 1 times the derivative of the top minus the top times the derivative of the bottom all over, and then we have the bottom squared. Okay, so if we simplify this, that gives us what? A minus 2x plus 2, and then plus 2x all over x minus x plus 1 squared. And our 2x's, let's do this in a different color. That 2x cancels that 2x. And so then we get a 2 over minus x, right, over the minus x plus 1 squared. Now we could also write that as 2 times minus x plus 1 to the negative 2. Okay, so that would be another way to write it. And I write that because I know that in a little bit, if I use that, it's going to be easier to do the second derivative. All right, so, but this place is where actually, that's a plus 1. I don't know why I have a minus 1 there. And this one, this is going to be a nice thing to figure out where our partition number is. Well, our partition number is going to be what? Well, x is equal to a 1 again, because if we plug a 1 in here, we get 0 in the denominator, and the critical number, remember, this is going to be, it's not going to be derivative at that point because we can't have a 0 in the denominator. So if we do our sign chart, which is what we're supposed to do next, at 1, can't take the derivative there. And so now we plug in, say, maybe a 0, maybe a 2. And again, this is f prime. So if we plug a 0 in here, we get 2 over a 1, which is 2, which is positive. So over here, it looks like they're positives. If we plug a 2 in here, that's going to be a minus. But when we square it, it's going to be positive, and it's going to be positive. So it looks like it's going to be positive on this side as well. Okay. So what does that mean? Well, it's increasing here, and it's increasing here. And what else can we say? So if we had to write that out, we could say it's increasing from negative infinity up to 1 and from 1 to positive infinity. Okay. Now, because we're not changing sign, there's going to be no extrema points, no local extrema. So no local min or local max. And what else can we say? I think that's about all we can say on that point. All right, so now that's what number 2 said. So now let's go to number 3, which said now let's find the second derivative. And again, I say I'm going to use this one because it's going to be easier. So I bring that negative 2 down here. So I get what? A negative 4 times a negative x plus 1 to the negative 3. And well, and then we have to take the derivative of what's inside here. So that's a negative 1. So we can't forget that. All right, so now we have a negative 4 times a negative 1, so that's going to be a positive 4. And then if we put it on the bottom, minus x plus 1 to the positive 3. So again, either way, it won't matter which way we do it, but this one is going to help us for getting a lot of this extra stuff. This one would only help us if we had to take the third derivative, okay? All right, so what's our partition numbers again? Well, again, x is equal to 1 is going to be that, and it's going to be a critical number. Well, it's going to be a ND because again, we can't have that be the 0. And so if we plug that in here, we have a 1. This is the f double prime. This is 0. This is, say, 2. All right, so if we plug in a 0, it's going to be positive. And again, this is ND. So we're going to have positives over here. If we plug in a 2 here, that's going to give us a negative 2 plus 1 is going to be negative 1 cubed is negative. So on this side, it's actually negative values. Okay. So what can that tell us? Well, that can tell us here we're going to be concave down because I'm out of room. Oh, wait, up, sorry. Why did I write down? Because I was writing below, so I said down. All right, so that's concave up because it's positive, and this is concave down because it's negative. Okay. All right. Now, if this had been a 0, we'd have an inflection point because it would be going from positive to negative. Because it's no derivative at that point, we can't say that. And so what we can say is it's going to be concave up from what? Well, negative infinity up to 1, and concave down from what? 1 to positive infinity. Okay. Now we have to draw what our graph looks like. We might be able to get it up here. All right, so 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And again, these are just going to be rough sketches. And so let's change colors for asymptotes. Let's do a red. We have a horizontal asymptote at y equals negative 2. So something like that. And we also have vertical asymptote at x equals a positive 1. So something like that. All right, now what do we want to do? Maybe we can draw a different color here. I don't know what we want to do. We'll just go back to this color. Maybe it'll be visible. Now, what points do we know? Well, we know this one here because that's our 0, 0. Is there any other points we know for sure? For sure, not. Doesn't look like it. So now what we need to do is just kind of plug in points. And so what we can do is we can come up with some X and Y values and then go from there. So say we have a -2. So let's do something over here because we're going to know it's there. Okay, so that's going to be a -4 over 3. So that's going to be -4/3. So -4 over 3. So -2 is going to be a -4/3. So maybe about there. All right. -1. What's that going to be? Oh, that's going to be -2 over 2. So that's going to be a -1. So -1, -1. And so I think probably that's good because what we know is going to it's going to go concave up. Going to go through those points and we have the asymptotes we have to kind of follow. Okay. Now let's think about something down here. So let's go to 2. So if we put 2 in here, what do we have? Well, that's going to be 4 over -1. Wait, yeah, 4 over -1. So it's going to be -4. So 2 and then -4. Well, oh, we went back up here. Over here. There we go. And let's say we go to 3. So that's going to be 6 over that. So that's going to be a -3. And so 3 and then -3. And this one should be, it says concave down over here. And so it would make sense we're going to have something that looks like that. Okay. And so it's a lot of stuff to get it all done, and then we get our graph that looks like that. Now, could we just plug that in our calculator and get a graph? Yeah, we could, but this is a way to go about it using the calculus to get there. All right, so let's stop there and we'll come back for another one.